Hi, my name is Jim, and today we're going to be talking about a circuit configuration that leads to series resonance. And it has some very unique properties which are very useful. And everybody's been exposed to resonance, say the mechanical resonance. Good example would be the pendulum on a clock. If you're driving your car and you hear a rattle in the trunk at a certain speed, and then that goes away as your speed increases, that's a parasitic resonance. And in our case here with electronics, resonance occurs when the magnitude of the inductive reactance equals the magnitude of the capacitive reactance. So if we wanted to find out what that frequency would be, what we would do is set these magnitudes equal and then substitute in their respective equations and then solve for F. So what we see here is that I've multiplied both sides by 2 pi Fc, leaving 4 pi squared F squared times LC. And then to isolate F, divided both sides by 4 pi squared LC, and I have F squared all by itself. I need to get F alone, not with a square, so taking the square root of both sides leads to the series resonant formula, Fr equals 1 divided by the quantity 2 pi square root of LC. Now the series resonant circuit has a cousin in the parallel resonant circuit, and this formula applies for the parallel resonant circuit for quality factors, which we'll talk about shortly, greater than 10. Other than that, there are 3 definitions for resonance in a parallel resonant circuit, so it's not as nice as mathematically as series resonance. So if we take a look at a curve here, an impedance plot of this, notice we have F on the axis down here, the x-axis, and Z is a function of this, and what we're going to do is change the frequency of our source here. And then as we do, the frequency increases and the capacitive reactance dominates because F is low, hence X sub C is high. So most of the voltage will be dropped across the capacitor, and then we'll reach a point where the magnitude of X sub C and X sub L are equal, and that'll be the lowest impedance point in the frequency sweep. In that case, the total impedance Z is equal to a resistive R, that guy. As we continue to turn up the frequency, what we see now is that the inductive reactance will dominate, because if F goes up, X sub L goes up. So now more voltage would be dropped across L as opposed to dropped across C or across R. So that's what a series resonant circuit looks like from the standpoint of impedance. Now if we look at a current plot, well, it's not too surprising to see that it's opposite of the impedance plot, and we reach the maximum current flowing in the circuit at the resonant frequency, and that current would simply be equal to the V over R, and that would be at 0 degrees. It would be a current which is in phase with the source voltage. And if we were to take a look at V out, and remember that's across the resistor, it's basically the same shape, because the output voltage will be directly proportional to the current I. So that would be the output across the resistor, and that would also be at 0 degrees. So now we come down to quality factor, and that means several things. In short, it's the value of X over R, and I've shown the absolute value there just to be safe and throw out the angle. And the higher the X is with relation to R, the steeper the curve is, the more peaked it is. So if this resistance were higher, what we would see is a wider but less peaked curve. And that has some interesting consequences coming up a little bit later. Q also equals the bandwidth of a circuit divided by the resonant frequency. And as we'll see, bandwidth is where the voltage drops by negative 3 dB, or drops by 3 dB, or the 0.707 point, not to be confused with the RMS operator. So if we take an expanded look at V out, and this is the voltage across the resistor relative to the maximum, what we would see if we decreased or increased the frequency a bit, we would end up to a point where we're dropped to 70.7% of the maximum voltage across this. and that equals a negative 3 dB point. So commonly this is referred to as the bandwidth of a circuit. It's its definition, is when the output voltage drops by 3 dB. So what we see is that it is from one side to the other would be the bandwidth, with FR sitting sort of in the middle. And if we'd like to think about a useful use for this circuit, it would be tuning in a radio station. Suppose we have 1220 here, and we want to select him and listen to him, and 1100 is here and 1300 is here. The output voltages of these two guys are going to be discriminated against by the resonant circuit. Hence, would let our 1220 come through much more strongly than the other two signals. So the resonant frequency is not the arithmetic mean between the upper and lower bandwidth frequencies, but it's a geometric mean. So if we wanted to find that, and we knew the upper and the lower, which we can easily measure in the lab arrangement, it would just be the square root of F upper times F lower. So it's not this many hertz above equals this many hertz below. So if we look at the difference in quality factor here, and what I've shown in blue is a high Q circuit, and what we see is that the bandwidth is relatively narrow compared to a lower Q circuit, which spreads out more. And the difference in amplitude here is not designed to be misleading. It's the difference, the 3 dB point is the difference between the maximum of green down to here, and the difference in the blue, the higher Q circuit, is its maximum down to here. Now if we project these 3 dB points down there, we can see the bandwidth of the green trace is wider than that of the blue trace. Now let's think about an AM radio for a second. The bandwidth by FCC standards is 10 kilohertz, and the maximum frequency that can be transmitted is 5 kilohertz. So what we want to do is have a bandwidth, basically it would be a rectangle, but we can't do that. There would be 5 kilohertz on each side, or 10 kilohertz total. Now in the practical world, if I made the Q real high, what that would do would be cut off the components of the music or speech in or around 5 kilohertz. So it would be a poorer frequency response than it is already, 5K compared to FM, which is 15K. But what I would get is good selectivity, which means that I could more easily discriminate between the station I want and adjacent stations. And likewise, if I had a low bandwidth, a low Q circuit, it would open up my bandwidth a bit, which might be good, but it would also allow interferers, adjacent interfering stations, to get into the main station I want to listen to. So not too high, not too low, just right is kind of important. Now let's take a look at the voltage output across R at resonance, and we'll use a standard voltage divider rule to see this. So VR is going to be equal to the source voltage, and the resistor bumps up against ground, so we'll just put him on top, and then in the denominator we'll have Z total, which is R minus JX sub C plus JX of L, and since these two add to 0, in resonance the magnitudes are equal, what we get is R over R, which is equal to 1, so VR is equal to VS. So it's as if there were no reactance in the circuit at all. Now if we're below resonance, that'll be to the left of the resonant point, what we have is VR would be equal to VS again, outputs across VR, but now what we have in the denominator is resistance minus J, the difference between the capacitive reactance and the inductive reactance, and below FR the capacitive reactance will dominate because of the relationship here. As F goes down, X sub C goes up. So what we would end up with here is a voltage divider with a resistive component in the numerator and in the denominator, along with a capacitive component, which would be the difference between X sub C and X sub L. Now V out across R above FR, and this would be the equation for that. Again, voltage divider Vs times R, and in the denominator now we have plus J X sub L minus X sub C, so this would be the difference. And this would be an inductive circuit because as F goes up, FL goes up. Oops, that's the wrong formula. Oh well, let's try again real quick. 2 pi FL. There we go. Oh, better. As F goes up, X sub L goes up. So most of the voltage is going to be dropped across the inductive reactance, and we're going to have a voltage across the resistance which lags Vs. And in both cases, by the way, VR is going to be less than Vs. It's not the case that we had in resonance. So taking V out across the capacitor, this leads some very, very interesting results. And this is at resonance, it's understood that. And I'm using a function generator here. And then later what I'm going to do is plug in an antenna symbol. And we'll say here that at resonance the inductive reactance is 10,000 ohms and the capacitive reactance is also 10,000 ohms. Only now we're going to take the output across the capacitor instead of across the resistor. So what we see here is Z total, again, is equal to R is equal to 200 ohms at 0 degrees. Just writing that down in polar form because we're going to be using it in a minute. And VC, which is the voltage across the capacitor, would be equal to the source voltage times the capacitor's impedance, Z sub C, divided by Z total, which we just found here. So that would be 5 at 0 times 10K at negative 90 degrees ohms, and that would be this value expressed in polar form, divided by 200 at 0 ohms, and that gives us an incredible output voltage, which seems unrealizable, of 250 volts at negative 90 degrees. So what we say here is we have a Q rise in voltage. Now what's the Q? It's 10K divided by 200 ohms. So we can get this amplifying effect, and it really happens. The only problem is in a radio receiver is that the L relates to the antenna length. And with an outdoor antenna for AM, for example, it would actually look like this. Now I've included R in here, as a loss, as you know, as part of the resistance of the circuit. And I've made the capacitor variable so I can tune it. And the input of any amplifiers that follow would have to be very high impedance so as not to load X sub C here, because that throws kind of a little variable in there which will reduce the gain. So we could actually use this circuit as a tuner and pick up some nice benefits from the Q rise in voltage across the reactive elements. But unfortunately, a parallel resonance circuit does not depend upon the length of the antenna. As a matter of fact, it can be built in, and hence parallel resonance circuits are almost always used in radio receivers. Now, to show a little bit of detail here, I've got some simulated plots. I'm just going to roll the camera up here a little bit. There we go. Make it a little bit closer. And the first, what we're looking at here is a series resonance circuit, or F, the resonant frequency is equal to 1 kilohertz. And I'm using the impedance blocks here. And if you use those, make sure you set some value for R. It cannot be 0 or your calculations will not work out right. So in the block here, the A would be equal to R, and I made that like 0.01 ohms, and then set the inductive reactance for 100K, and likewise for the capacitor impedance block. And notice this is A minus JB and A plus JB, and here's a V out across resistor 1. So the equivalent circuit of this I drew below because these blocks are a little bit confusing. It's nice that you can enter the reactance directly without having to figure out the C values like I would do for the circuit down below. Now this is a voltage plot across R, and what we see is that resonance VR here is 10 volts, which would be equal to my input voltage from the previous sheet. And we would kind of expect that, and notice that this voltage here is logarithmic. We need to pay attention to that. And now taking a look at the phase, we see some interesting things happen. This is sitting up here at plus 90 degrees, and the reason is that we're below resonance, and X sub C dominates, and that causes the current to lead the voltage, so we're plus 90 degrees, and it's relatively constant until we get to the resonant point, and then it drops real quick, and we would be picking up 0, to be right about there, at the resonant frequency, and then for frequencies above it, the inductive reactance would dominate, and then we're seeing output voltages that asymptotically approach negative 90 degrees. So a lower Q circuit would not have a transition as sharp as this. It would be more gradual, and also the skirts of this here would be a little less steep if the Q were not higher. Now if we take a look at the current plot, no surprises, it's the same shape as the voltage plot, and our peak here is 10 milliamperes. Again, this is logarithmic, and then what we see here is the same with the current as we had before, where the capacitive reactance dominates for lower frequencies, and the inductive reactance dominates for higher frequencies. And in the middle there, at resonant frequencies, I put a little line there. It looks resistive. So the phase shift would be 0 degrees. Okay, an impedance plot. Let's see what that's got to offer. So what we see for impedance is that we start out high, and this would be the capacitive reactance. And we reach a minimum here at resonant frequency, which would be 1 k ohms. And then as we proceed, the inductive reactance would dominate, so the impedance would get higher. And now if we take a look at the impedance, what we see is negative J down here, which would be the capacitive reactance at a negative 90 degrees until we get to the resonant point, and this is 0 degrees. And then above resonance, we're asymptotically really close to plus 90 degrees because the inductive reactance dominates. Now this is a lot of stuff coming at you quick, but if you think about everything up to this point in time, this should make sense to you. Finally, I'm going to take the voltage across the capacitive reactance, and in this case, very unrealistic, this would be the capacitor here, is that we're going to hit an output voltage of 1000 volts. Now, that's obviously not going to happen with a 10 volt input, but what we're seeing is a Q rise in voltage here, and that happens at 1 kilohertz. So this would be the general shape of things. And if we were to take the output across the inductor, it'd be sort of similar. This is the inductive reactance here, is we would get a Q rise in voltage at this point, and that also would be at 1000 volts. So we're talking about Q rises here. Is getting a Q of 100 is kind of hard, and realistically our input voltages are going to be a whole lot smaller than 10 volts peak, so we're not going to be seeing anything that's quite as fantastic. And the reason that the Q is lower is because inductors and its resistors typically limit that to some value quite underneath what we're talking about here. So that'll do it for today, and thank you for watching.